Hello, my name is Joshua and I'm going to present this work on the fabrication of a Schottky diode. We use a new cantilever-based printing technology for printing the contacts of this diode. Our device is based on a selenium-doped Fe2O3 material. Traditional microfabrication involves technologies such as photolithography. There are many processes that needs to be dealt with while using these technologies. I have listed a couple of them. However, these technologies are highly optimized. Currently, these technologies are very highly optimized to fabricate various devices that are required to produce highly packed integrated circuits. The main challenges addressed by these technologies are to achieve high cleanliness in the fabrication environment and also to increase the resolution of the miniaturized devices produced. In recent years, printing technology has become a popular alternative to photolithography for producing devices. The primary reason is because it relieves the use of high-end equipments involved in the fabrication process, such as sputtering. It also relieves complex processes involved for the same, such as etching and masking. I have summarized a couple of popular variations within the printing technology. The cantilever-based technique, which is used by us, is an additive technique to produce micropatterns having a feature size resolution of 0.5 to 1000 micrometer. We have created a novel variation of the cantilever technique called a microgirder variation. This technique is capable of producing patterns in the sub 10 micrometer range. In fact, we were successful in creating diodes with a spacing as low as 2 micrometer. The microgirder technology is highly simplistic in its approach and time efficient too. The average time required to fabricate our device is around 30 minutes. However, sometimes it can take up to an hour long. Our technology can integrate various incompatible inorganic materials to provide devices that would otherwise not have been possible using the traditional microfabrication techniques. Our technology is highly cost efficient with almost no wastage of material. In fact, one drop of silver ink is all that is required to print the contacts for the device on a silicon wafer. The fabrication process occurs in a two-step process. In the first step, we produce the silver electrodes using our in-house printing system. In the next step, we drop cast the dispersion of the material used for the device in deionized water. The selenium doped Fe2O3 material used in our device is synthesized using a two-step process. In the first step, we synthesize the dendritic alpha Fe2O3 using the hydrothermal synthesis. In the next step, we synthesize the selenium doped variant of the same using the two-zone furnace. We can observe the EDS of the material placed on a silicon substrate. As expected, the silicon corresponds to the highest peak as the material is placed on a silicon wafer. We can also observe that the selenium peak is relatively low compared to the other materials present. It is because the selenium is used as a doping material for this composite. The SEM image is also given. It has a leaf-like structure which indicates that this material has a high potential for gas sensing applications. The reason is because these structures like this can bond efficiently with selective gases that are required to be sensed. We have performed the electrical characterization for the Schottky diode that we fabricated. We used the thermionic emission model for characterizing our device. For the modeling, the base equation that we use is the following. In this equation, the important parameters that are required to be calculated by us is highlighted in red. A refers to the Schottky contact area, which is computed as 0.25 millimeter square, and the calculations of this is given in the figure. A double star refers to Richardson constant, and it is computed using the following formula with an additional parameter called the M star. The M star is the effective mass of Fe2O3. However, as we don't have any effective mass of Fe2O3 reported, we moved forward with the calculation with the effective mass of a material which is similar in stoichiometry. Eta refers to the ideality factor, and it is relatively easy to compute as we just require to extract the linear region of the lni versus v graph, and from that we can the slope of the graph gives us the value of eta. For the calculation of phi b, that is the barrier height, we require to modify the equation to the following format. What we basically do is bring the a star t square to the left hand side of the equation from the base equation, and then we take log on both sides, and after doing several algebraic exchanges, we get the following equation. The Schottky barrier height is computed as 0.72 electron volt, and the series resistance is computed as 159 kilo ohm. We obtain this from the intercept and the slope of the HID versus I graph. The graphs are shown as below, used for the calculation of the important parameters for characterizing or modeling the device. The first graph refers to the log I versus V graph. The second refers to the linear region of the log I versus V graph, from which the ideality factor is calculated. The third graph refers to the HID versus I graph for calculating phi B and the series resistance Rs. We have also verified the results that we obtained using the dV by dlni versus I graph. The equation which we have obtained from HID is manipulated to obtain the following equation. From this plot, we obtain the eta value as 3.8, which is closely correlated to the previous eta we got from the thermionic emission model, that is 3.44. Also, the series resistance doesn't change by a huge margin. The series resistance obtained by this verification method is 166 kilo ohm, while we obtain the series resistance of 159 kilo ohm via the thermionic emission model. Concluding this presentation, our work contains three novelty. The first is that this is the first ever printed silver electrodes using the state-of-the-art micro girder cantilever-based in-house printing system. This is also the first ever fabricated selenium doped variant of the Fe2O3-based Schottky diode. The device is thirdly, the device is modeled using the thermionic emission diode current model to compare the experimental results. Future works involves applications in gas sensing. In fact, we have carried out the experiments required for this and have obtained promising results. We also require to calculate the actual M star or the effective mass for the Fe2O3 material. We realize that we have taken the effective mass of a different material for the calculation of this selenium doped Fe2O3 based Schottky diode. However, we expect the effective mass of both the materials to be of the same order and therefore can be approximated. However, further experimental data is required for computing the actual M star for this particular material so that it can be used for further applications. Since the microgirder cantilever-based fabrication technology is still in its early stages, work on further optimization is being carried out. The work presented in this, the results presented in this work is preliminary in nature. The fabrication technology, from the fabrication technology perspective, we need material optimization, printed material optimization to make ideal diodes using new materials. Development on printed material optimization is promising as the microgirder technology is capable of printing incompatible organic and inorganic materials onto substrates. Apart from new material investigation, we also need to enhance the material properties to improve the interface characteristics of these materials with metal-metal contact. These processes can potentially bring down the ideality factor of the devices fabricated using this technique. Thank you.